One of the most difficult subjects that students come across in their first time at chemistry is the notion of significant figures. And I think one of the reasons for these difficulties is that professors so rarely take the time to really dig into the question of what are significant figures and why do we even bother with them. And the title of this PowerPoint is essentially the why answer to that question. Why do we deal with significant figures? And significant figures are a solution to the problem of measurement. So what do we mean? Well, measurement is actually something we do when we artificially assign a number to something that's not easily quantifiable. So if you think about it, have you ever tried to, and you can feel free to turn on your microphones. I'd actually love to hear your voices and we can interact more personally that way. I think it's a lot more fun. But have you ever tried to, maybe think about it, like how much or how many water is there in a cup? You might be like, well, how big of a cup? Well, that's a good question, isn't it? You have bigger cups, you have smaller cups. How much water, how many water is there? How many water? It doesn't really make any sense. Or how many brightness? How intense is the brightness? Can you give that a number? These are things that are not easy to quantify. So there's a lot of things like that, even some basic things that you automatically think of in numeric terms because we're so used to quantifying them. So from the earliest history, we've tried to find ways to quantify things that are not naturally countable. If you think, even in terms of biblical times, the notion of a cubit. So the cubit was an ancient unit of measurement that was basically the distance between your elbow and the tip of your fingers. Now the problem is if you were a tall person or if you were a short person, if you were a child versus an adult, the length of your cubit varied widely. Your cubit would be very different than my cubit, okay? So it wasn't a consistent standard. But you needed to have some way to give somebody a certain measure of how long something was, what length. So over time, we've developed different standards, and the standard is basically something that we use to compare or quantify something not easily quantifiable. So everybody has to use the same standard if we're going to be able to have measurements that make any sense to each other. So the problem is whenever you're using a standard, the standards, you're never going to have a perfect measurement because nothing can be exactly 100% equal to that standard down to the last atom in terms of length or height or volume or whatever. So anytime we measure something, if you say how tall are you, you might say, well, I would say I'm about 5'8" or 5'9" actually. But maybe you're like 5'3". But the truth of the matter is when I wake up in the morning, I'm closer to 5'9", maybe even 5'10". But when I go to bed at night, I'm closer to 5'8". That's because my height changes throughout the day. But not only my height, if I tried to measure myself and 10 other people tried to measure me at the same time, they would all come up with slightly different measurements. Some would be the same, some would be different. It is because when we measure, we can never measure something perfectly. So that's where significant figures comes in. So there are different types of numbers. First, before we get into significant figures, we want to establish what we mean by types of numbers. So there's two types of numbers, exact and measured. Now, exact numbers are numbers that we can, in fact, clearly quantify. Like, for example, the number of people attending this session. It's not going to be 4.5 people. It's not going to be 5.5 people or 5.2. It's going to be a whole number. 4 or 5 or 6 or 7 people are attending this session right now. However, so those numbers, since they're exact and they can be counted, they have no error. They have no uncertainty. They are literally exact. Another type of exact number would be a definition. So by definition, there are 12 inches in 1 foot. Now, even though a foot and an inch are both measured values, they're based upon some standard. The relationship between a foot and inches is exact because it is by definition. Likewise, with a centimeter and a meter, there are 100 centimeters in 1 meter. That is an exact number because it is by definition. We define a centimeter to be exactly 1/100th of a meter. So they have no uncertainty, they have unlimited precision. Measured numbers always have a little bit of uncertainty. It's never exactly one thing or another. What we do with measured numbers is because things always fall in between the standards that we use. We measure all digits that are known with certainty and one estimated digit. So these are just some examples of counting objects. They're always exact. 2 soccer balls, 4 pizzas, things that we can count easily, or definitions. So let's check and see how we understand this concept clearly. 1 yard equals 3 feet. Would that be an exact number or would that be a measured number? What do you think? I egged it out. I'm seeing exact. No, that's good. And please feel free to use your microphone if you want. If you don't want to, that's okay. You don't have to. But what about the diameter of a red blood cell? Diameter of a red blood cell. Would that be exact or measured? Yeah, that would definitely be measured. Exactly. We have to measure how long a red blood cell is. Now, that's a tricky measurement to do, but it is a measured number. 6 hats on a shelf, exact or measured? Yep. And what about gold melts at 1064 degrees Celsius? Is that exact or measured? Yeah, that would be a measured number. Very good. Usually I get at least one person to say that's an exact number. But yeah, we have to measure the temperature. So you can't, there's no, and if you think about it, like just without some sort of a thermometer, this is also a good way to recognize that something's a measured versus exact, or recognize whether or not we need to use significant figures. If it's not something that you can simply count, if it's something that you need an instrument to figure out the number of, then that would probably most likely be a measured value or measured number. Okay, cool. So significant figures essentially tell you the precision of a measurement. How precise is the measurement? So it's the numbers that reflect the degree of certainty to which a value is measured. That's what it says here. And that's kind of fancy language. It's not necessarily clear what that means, but in practical terms, when you measure something to the appropriate number of significant figures, you're measuring all digits that are known with certainty plus one estimated digit. So even this as a description is going to be a little bit unclear, but we're going to do some practice problems and do lots of examples so that you get a clear idea of what we're talking about when we say measure all digits known with certainty plus one estimated digit. Digital instruments oftentimes will measure for us to the correct number of significant figures, but we use a lot of numbers. Sorry, I tripped over my tripped over my microphone. Uh, we use a lot of non-digital instruments in the lab, including meter sticks, graduated cylinders, thermometers, etc. So there's a number of non-digital instruments that we're going to be using, and we have to be able to measure those to the correct number of significant figures. Also, truthfully, even if we had all digital instruments for each of these things, it's still helpful to understand significant figures because it does have a, when we're crunching numbers and doing calculations, it does become important that we understand why we use the rules that we do. Okay, so here's an example of measuring with significant figures. So here's a graduated cylinder, and this is blown up. It's blown up into this over here. And you can see that this is 15 and this is 20. So by extrapolation, you could probably assume that, hey, this is going to be 16, right? This is 17, 18, 19, and 20 milliliters, okay? So whenever we measure a liquid in a graduated cylinder or something like that, we always measure from the bottom of the meniscus. Now the meniscus is this lowest part of the dip. So a meniscus kind of tends to look like this. It's like a dip on either side of a graduated cylinder. And we'll measure from the bottom of that dip. So in this example that I've drawn here, bottom of the meniscus would be like right there. Now over here at the bottom of the meniscus, it's a little bit trickier, but you can kind of see, go across. The dip is not too significant for larger graduated cylinders. It goes up a little bit at the edges, but it's not a huge drop into the middle. But you always measure from that lowest point, or from the middle. All right, so if I'm measuring from the bottom of the meniscus, I can see clearly that this is in between 17 and 18. So I know, for example, that the volume is, I know the tens place is certain. I know that it's between 10 and 20, okay? So that tens place is certain. I also know the ones digit for certain because it's clearly between 17 milliliters and 18 milliliters. What I'm not certain about is the tenths place. The tenths place is one I have to estimate. Now, if you were to estimate this, what would you say? If we cut the volume in between 17 and 18 up into 10 equal parts, where would you say that bottom of the meniscus is? What do you think this is? 17 point what? Take a look. 17.5, 17.6? Absolutely. And both of those are perfectly acceptable answers. Both of those are perfectly acceptable answers. 17.5, 17.6. And notice they're not the same. That's because the estimate is not perfect. It could be a little bit more or a little bit less. One could even make the case that maybe this is like 17.4, although in truth, it's probably almost certainly 17.5 or 17.6. Now, another thing that we have to be careful of is what's referred to as parallax errors. Parallax errors is when what happens when you read the bottom of the meniscus, read the volume at an angle. Because of the distortion of the lens effect of the glass, it'll cause you to think that the volume is less than or greater than what it actually is. So if you look at something above the meniscus, it'll look like here. Oh, whoops. If you look at something above the meniscus, it'll look like the measurement is here, and you'll end up with a low reading. If you look at it too low, it'll end up looking like it's here. It'll be too high of a reading. You have to look at it at eye level in order to get an accurate reading of the volume. So for water, it's a always read from the volume at the center of the tube, so it means reading from the bottom of the meniscus. So if you have a mercury thermometer, notice it's kind of interesting that a mercury thermometer dips up like this. And as a result, you read from the middle, you read from the top of the meniscus, but for water, you read at the bottom. Essentially, though, you're always reading from the middle of the tube. Okay, so let's do some practice. So these are two images of measurements of volume that you might see in the lab. Go ahead and take a moment to estimate between the smallest markings and give a measurement of the volume in each of these cases. We'll give you a minute to work it out. All right, let's see what we got. Okay, got one person. We ready to rumble? All right, let's take a look at it. So we have one person who are at 52.9. By the way, the chats are anonymized, so in the video. Does anybody else know, or does anybody else have a guess as to the first one? We have a 52.9. Anybody else have anything different? Well, let's take a look. Or does anybody need more time? Do you need more time, or do we want to just kind of go into it? Okay. Thank you. There's a difference in the second one. Anybody else? Oh, sure, absolutely. And why not? Let's go ahead and take a look at it. So if we're looking at this, we should notice that this here is 55. And if we're reading the bottom of the meniscus, that's going to come off like right at about here. Okay. Now, if this is 55, and this is 50 at this line down here, then this is in between 52 and 53. So it is 52 point something. Now, if you're reading it from the bottom of the meniscus, I can understand why you'd say 52.9. And that's kind of an acceptable answer, but I would say it ventures a little bit on the high side. It's clearly above the halfway point, so it's definitely above 55.5. And it definitely seems to be closer perhaps to the upper part, but I would say honestly 55 or 52.7 or 52.8 is probably more likely. But once again, there is some flexibility there. So it's not that 55 or 52.9 is wrong. It just may not quite be the best estimate. I would definitely say that 52.7 or 52.7 or 52.8 is probably a better estimate. So 52.7 to 52.8. Although if I was taking a test, or if I was giving you a test and you did 52.9, I would not mark it wrong. I would accept it. It would not be, that would be okay. Now, let's take a look. Okay, so for the next one people struggled with just a bit more. Now, here's the deal. This is seven here. This is seven. And then you have the 8 marking here. This is 8. And then 6 is down here. Okay. So the smallest markings are, there's 5 markings between 6 and 7, and 5 markings between 7 and 8. So if I'm looking at this, this would be 6.2, 6.4, 6.6, 6.8, and 7. Okay? Now the bottom of the meniscus is clearly between 6.6 and 6.8. The 6, though, is pretty certain. It's the tenth place that's estimated. The small, you always want to, and actually even the tenth place, it's pretty certain as well, because it's clearly between 6.6 and 6.8. So that tenth place is actually pretty certain as well. In a case like this, since the values are to the are 0.2, each one of those spaces is worth about 0.2. You can probably estimate to the next to 1/10 of that, to 1 degree beyond the smallest markings. You can usually estimate you can always estimate to 1 degree beyond the smallest markings. Since the smallest markings are worth 2/10, then you can estimate to the hundredths place. You can estimate to 2/200. Now, if it was 0.5, then yes, you could probably you could only estimate really to the tenths place. But since it's 0.2, you can really kind of estimate to the hundredths place here, and that would be the more appropriate thing to do. And the bottom of the meniscus is right about here. So if I'm looking at the bottom of the meniscus here, it's definitely closer to 6.6 than it is to 6.8. And if I look at the halfway point here, change my color just a little bit. Green. Halfway point in between these two lines is right about here. It's definitely, I look at the halfway point, it's definitely a little less than halfway between the 6.7 and the 6.6. I'd be tempted to say that this was 6.64, maybe 6.63 or 6.64. You could even say 6.62, but I think 6.63, 6.64, that would probably be the best estimate here. Does that make sense? I realize that that's not an easy one to estimate. Any questions on that? Okay, cool. So let's take a look at what comes next. So when estimating between length, this is a little bit easier to see. Um, Once again, we estimate between the smallest markings. If we're saying that these are centimeters, which in this case, that's what they're supposed to be, we're going to say this is just a really blown up ruler. So this is 1 centimeter, this is 2 centimeters. So that 1.1, 2, 3, 4, 5, this is 1.5. And you can see that this is in between 1.6 and 1.7. 1.5 is right here. So there's no smaller markings between 1.6 and 1.7. The tenths place, it is certain, is 1.6 something. So it's 1.6 something. And so we estimate to the hundredths place. In this case, it looks to be closer to 1.7. So we could say that this is 1.67, or we could say 1.66. Either one of those is perfectly fine. There's a little flexibility. Since that last digit, the seventh, is uncertain, it is uncertain, it is estimated, we have to stop our measurement there. So what is the length of this wooden stick based on this ruler? What would be the length of this? You can type your answer in the chat, or you can speak it out loud if you wish. All right. Okay. Got 4.55, 4.6, 4.56. Very good. Yeah, I would definitely say this is going to be 4.56. So it's in between the 4.5 mark here. It's in between the 4.5 mark here and the 4.6 mark here. We estimate between, so it'll be 4.55 or 4.56. Looks just a little bit beyond halfway. You wouldn't be wrong if you said 4.55. Very good. So, in person, we had measuring stations that I had people measure. Unfortunately, we're not going to be able to do that online, but we can get to the calculation aspect of this. So we have, it says below are two measurements of mass of the same object. The same quantity is being measured, is being described at two different levels of precision or certainty. So in the first case, the uncertain digit is the hundredths place. That means that this is plus or minus 0.01, plus or minus 100. In the second case, the last digit that is written is in the 100,000th place. And that means it's plus or minus 1/100,000th. The very, very significant differences between these two numbers. The second one has a much higher degree of precision, a much higher degree of certainty than the first. So we have to keep track of our precision, our certainty, when we're doing calculations and when we're looking at numbers. So you've just gone through how to measure with the appropriate number of significant figures in some of the examples that we did. However, we also need to, when we're given numbers, when we're given measured values, be able to determine how many significant figures there are. And that brings us to the rules of zero. So when we're given a measured value that's already been recorded, all non-zero numbers are assumed to be significant. However, for zeros, we have to use the following rules. The leading zeros are never significant. So if you see 0.00259 here, none of these zeros are significant. You'd only have three significant figures. That would be these three. Because zeros before the decimal point, or zeros, yeah, zeros that are leading zeros are always place value holders. They're just holding place value. They're not actually telling you the degree of precision. Sandwich zeros, or zeros between non-zero numbers, are always significant. So these are always significant. Yeah. So this would have a total of 5 significant figures. And then the last rule is um, that trailing zeros are only significant if the value has a decimal point. So trailing zeros would be zeros like these ones here and these ones here. They're zeros at the end to the right of to the right of non-zero numbers. So zeros after the last non-zero number, or to the right of the last non-zero number. These are only significant if there's a decimal point. Notice it does not matter if the zeros are before or after the decimal point. It only matters that there is a decimal point. So in this case, this has 3 significant figures because these zeros are trailing. They're at the end of, they're after the last non-zero number, and there's no decimal point. However, if I were to put a decimal point here, this would have 5 significant figures instead of 3. So, but as it is, it only has 3 significant figures. Okay. The other one, this has 5 significant figures. And one of the reasons you can actually kind of tell is because significant figures or significant zeros are almost never place value holders. And what that means is this. If I took away these zeros, this would still be 12.5. It would still have the same numerical value. However, the zeros here indicate the level of precision. If it was just 12.5, it would be plus or minus 0.1. But since it's 12.500, that means it's plus or minus 0.001. So trailing zeros are significant if there's a decimal point, but they're not significant if there's no decimal point. So let's look at some examples here. How many significant figures are in this first one? If possible, it would be great if you could go on your microphone. That way I wouldn't have to switch back and forth between the PowerPoint and the Blackboard Collaborate chat window. How many significant figures are in this first one?
6.
Very good. 6. What about the second one?
3.
3, exactly. So this is 3 because the leading zeros are not significant figures. What about the third one?
5.
5.
5, yep. The leading zeros are not, but the trailing zero is. So this is very good. All right, what about this one? What about 48,000 with the decimal point at the end? How many significant figures is that going to be?
5.
5.
5, very good. Trailing zeros with the decimal point counts. What about this 48,000, the second one?
2.
2. There's only 2 significant figures. Without that decimal point, this is basically saying this is the last significant figure, which means this number is only accurate to the nearest 1,000. This would be like you're estimating the amount in a crowd. It's 48,000 plus or minus 1,000. Well, if you're taking tickets and you counted the tickets, then maybe it's 48,000 plus or minus 1. So maybe a person got in here or there without a ticket, but for the most part you have an accurate count. However, 48,000 plus or minus 1,000, that's not very accurate. Not very precise, shall we say. So very good. Yeah, that's only 2 significant figures. Now, sorry, I cheated. It's 4. This is because numbers that are in scientific notation This last part here, this does not affect significant figures in any way, shape, or form. The times 10 to the power, all that does is indicate place value. It's the same as if I had trailing zeros, like these ones here, or if I had leading zeros, like these ones here. The times 10 to the 6, all it does is indicate the place value. So it is not important. It's not, well, it is important. It is important because place value is important, but it's not significant. And so that's actually another good point I wanted to make. Just because a number is not significant does not mean it's not important. If you don't include those non-significant zeros, it'll mess things up very, very much. So what about this last one? How many significant figures are in this last number?
6.
6. Very good.
And I just want to ask a question real quick.
Sure, go ahead.
On the scientific notation, so you said, let me get that corrected. Scientific notation does not affect place value?
Oh, no, well, this
Or
last part of the scientific notation, it indicates place value. Whoops. This last part of the scientific notation, it indicates place value. The first part of the number, the only part of the number that actually determines the amount of sig figs is the first part of the number. So when you have a number in scientific notation, only the first part tells you the number of sig figs. The times 10 to the whatever, that just tells you the place value.
place
So
value?
this part tells you sig figs, and this part tells you place value.
Okay, thank you.
No problem. And I should actually probably ask this because it's not an obvious question, because they don't really teach this in schools anymore, and I don't know why. But do y'all know what I mean when I say place value? Would anybody like me to go over go over quickly what I mean by place value?
Sure.
You're good?
Yeah, might as well do a refresh on it.
Okay, sure, no problem. So, um, when talking about place value, um, this is what we mean. This is something that used to be covered in elementary school, but hasn't in many, many years. And I'm not sure why they did away with it, but let's just say, for example, you have a number, and I'm just going to pick a random number, 1, 2, 3, 4, 5.678 Okay, so place value is essentially, it simply refers to um, the place, or how much, if I increased or decreased the number by one in that digit, how much does it change it? So for example, if I change this number, increase it or decrease it, I'm changing it by a value of 1. So this is called the ones place. If I increase or decrease the 4 up or down, so I change that to a 5 or a 3, then I'm changing it by tens. So this is going to be the tens place. So these values, they're referred to as place values. Okay? And zeros that are not significant are oftentimes place value holders. They hold place value. You see that with things like this, these leading zeros, they're place value holders. They hold place value because if you remove them, it changes the entire value of the rest of the numbers. So they are important to keep in. You must keep them in. Um, and the reason why I emphasize this place value thing is because it does become even more important later when we're doing calculation. So this, if I increase this 6 up or down, this would change it by 0.1 or 1/10. And so this would be the tenths place. And so on and so forth. So there's the tenths place, the hundredths place. So this would be the 100ths place. And then there'd be the thousandths place, and then the 10,000ths place. And on the other end, after the tens place, this would be the hundreds place, hundreds, as opposed to hundredths. But you all kind of get what I mean?
Yeah, thank you.
So yeah, so this is place value. So there's the hundreds place, the thousands place, and the 10,000s place. Um, usually, yeah. So it's important to understand what's meant by place value, especially if we're talking about the relative magnitude of the different place values. So for example, the hundredths place is smaller, 1/100th is smaller than a tenth. So a tenth is going to be the larger place value. One's place is larger than a tenth, so one is the larger place value. And we'll go into why that's important in just a little bit when we do addition and subtraction. For now, let's go to the next slide, because this is where everybody gets messed up, rounding. So let's round. So if we want, a lot of times when we're doing calculations, we end up with a number in our calculator that's pretty big, and we may only need a certain number, may only need like 4 significant figures or 3 significant figures. So if you're given a number in the calculator like this one here, then if you wanted to round that to the appropriate number of significant figures, the first thing you would do is you would go left to right until you reached 4 significant figures. So 1, 2, 3, 4. This last significant figure, the reason it's darkened is because this is our estimated digit. This is our last significant figure. So the estimated digit, the last significant figure, gets rounded up or down based on what comes after it. In this case, what comes after it is a 0. So is that going to round this 5 up or down?
It
In
doesn't
other words, is that 5 going to become a 6 or is it going to stay a 5?
say a 5.
It's going to stay a 5. So this is going to be, to round it to the correct number of significant figures, this is just going to be 4,965. What if I round the next one? So this is, once again, I'm going to go left to right. I'm going to go left to right, underline my first 4 significant figures, 1, 2, 3, 4. This last one is my estimated digit. This is where I cut off my number. I have to round this up or down based on the digit that comes after it, and the digit that comes after it in this case is the 8. So is this, when I say rounded up or down, what I'm really asking is this 7,000, or is this 780,582? Is that closer to 780,500, or is it closer to 780,600?
780,600.
Exactly. So this has to be, this would be rounded to 780,600. The most common mistake that I see with students is that they'll see something like this and they will round it and they'll write it as 7,806. What's the problem with that?
It changed to 7,800.
Yeah, exactly. If you had $780,000 in the bank and they said, "Oh no, you only have 7,800," you would be ticked, right? You'd be upset because they just stole your money.
Right.
So don't steal people's money. Don't take away those zeros, okay? If you if you have those trailing zeros are necessary to hold place value. So when you're rounding these numbers to a certain number of significant figures, always make sure that you add whatever zeros are necessary to hold place value. In other words, to keep the place value the same. In this case, if I started out with this 7 being 100,000, that's in the 100,000th place, I need that 7 to still be the 100,000th place after I round it. Or if you want to look at the last significant figure, the last significant figure is this 5. That's in the hundreds place. If that was 100 before, it still has to be 100 afterwards after I round. I can't have it be 1. Okay, what about this last one? What would this become?
That will go up to 2,000.
That will go up to 2,000. So would I write it just like this? 2000?
No, you would put the decimal after the less or the zero
Why do I need a decimal at the end?
because there was a decimal in the original. Um, I don't know how to explain that further. I just know because it's in
No,
the
you are correct. You are correct. Basically, what it comes down to is this. There are four significant figures here, right? The last significant figure is in the ones place. The last significant figure still needs to be in the ones place. So, if the last significant figure needs to be in the ones place, if I just wrote it as 2000, that would only be one significant figure, right?
right.
And so that means this would be the last significant figure. That's wrong. The only way I can make that last significant figure the ones place is if I put that decimal there. What about if you had a situation like this? What about if you had 24,586, and I rounded that to four significant. Well, actually, ooh, no. Let me change that. 24,599. What if I rounded that to four significant figures? 1, 2, 3, 4. So it would be what?
20.
What would that be? By the way, can you all hear me okay?
Yes.
Okay, good.
So it's gonna go to 24,600.
Okay. Now this is wrong. Why? What's wrong with this number? I was trying to round it to four significant figures. What's wrong with this number?
So would it
How,
be 26?
how
Is it
many
not?
significant figures is this?
2, 3.
It's three. It's not four. In this case, there's actually no way to express this in normal notation with the correct number of significant figures. You can't do it. If you
Right,
put a decimal at the end, the problem with that is that you have five significant figures and I only want four. If you don't put a decimal, you only have three. The only way to write this number correctly is to use scientific notation. So the only way to express this correctly would be to write it as 2.460, well, what the heck? 2.460 times 10 to the fourth. That would be the only way to write this with the correct number of significant figures. You will rarely, if ever, come across that situation. You'll probably hit it once in a great while, but sometimes you do need to use scientific notation to express a number with the appropriate number of significant figures. Okay,
okay, can I just ask one quick question?
no.
Um,
No, just kidding. That's totally fine. Go ahead.
so on that for the 24,599,
Hmm.
rounding that up, what stops us from, because what I was trying to do, I was rounding, so I rounded the 9 up to, so changed to 0 and then the 5. I was rounding all of them up. So then change the 5 to a 6, the 4 to a 5. So I know that's, I guess, I don't know why I was trying to do that.
Yeah, the tricky thing here is when you're um when you're doing this, You can't do serial. You got to be careful about not doing serial rounding. That's like serial murder with numbers. Like for example, so like for example, if you're gonna do if you're like if you had a number like this, you had 24.449. Let's say you had to round it to the tens place. I can't round this up and then cause that to round this up. I can't do that.
Okay.
Uh, I can, whenever I'm rounding, I always look at the last significant figure. In this case, the last significant figure, if I was to do three sig figs, let's say if I was to do three sig figs, the last significant figure would be this 4. I could only round it up or down based on what comes after it. What comes after it is the 4. And so since what comes after it is the 4, you'll just go ahead and keep it 24.4. It doesn't matter what comes after that.
Okay.
Does that
Thank
help at all?
Yes, sir. Thank you.
And by the way, I'll also say with this number over here, this 9.95, the truth is when a number ends exactly at 5, so the number after the last significant figure in this case is this 5. And actually, I should probably undo that. But essentially, whenever you have a perfect 5 like that, there's actually different schools of thought in this. Technically speaking, statistically, you're supposed to use what's called the rule of perfect fives, and that basically says that if you're rounding and the number after the last significant figure is a 5 with nothing after it, if the number is odd, you round up. If the number is even, you round down. That is because a perfect 5 is exactly halfway between the number above and the number below. And so statistically, you want it to go up. If it's perfectly halfway, if it's halfway between, exactly halfway between the number above and below, statistically, you want half of the time for it to go up and half the time for it to go down. And so that's why they use this rule of perfect fives. However, your professor is not going to expect you to know the rule of perfect fives. As far as your professor is concerned, if you see a 5 after the last significant figure, always round up. Okay?
Thank you.
Yeah. See a 5 after the last significant figure, you always round up. Whether or not there's anything after it. That'll just keep your life a little bit simpler. Okay, so let's take a look at this next one. Go ahead and do these next 5 here. Everybody take a moment and just round these real quickly. We'll give you a minute. We'll give you a minute. I don't want to take too much longer than a minute. And whenever you've done them all, go ahead and type ready into the chat, or just tell me you're ready, and we'll go over them. Got one. All right. Let's dig into this. Now, we're don't want to rush any of you, but I also want to make sure we get into some of the other stuff too. So, first one, 1.55, 1.5587. This should have been 1.56. 3 significant figures. The 8 rounds it up. Next, 0.00374, first 3 sig figs. After the 4 is a 2, rounds down. 0.00374. Now somebody put 0.004. Don't you lie to me. 0.004. Didn't you put that? Somebody did. Yeah, I'm telling you. I know there is one of these somewhere. Remember, those leading zeros trick you. They are not significant. Don't let them trick you. Leading zeros are never significant. That is not the right answer. There we go. Next one. What'd you get for that one? Yeah, very good. 1,370. Very good. Now I gave away the rest of them. Gosh darn it. Um, anyway, 128,522. Those 128. You're going to round that up because of the 5 after it. That'll be 129,000. That's probably one of the trickier ones. Remember, you need to add the zeros to hold place value. Did anybody get that one right? Get 129,000? I hope so. I hope so. We got, okay, cool. Yeah, awesome. Good job. All right. Now, we also have 1.67 times 10 to the 6th. That one shouldn't have been too bad. Hopefully you guys got that one. All right. Now let's go ahead and take a look from here. Let's take a look at adding and subtracting with significant figures. So, here we go. So when you're adding and subtracting, what you're adding and subtracting is actually, you're adding and subtracting uncertainty. So what you have to do is you have to look at the place value of the largest uncertainty. So the general rule is the sum or difference of two or more measured values must have the same precision, same uncertainty as the least precise measurement. The least precise measurement is the one with the greatest uncertainty. So if I look at this first number, 124.56, the uncertainty is in the hundredths place. 4.5, the uncertainty is in the tenths place. This has an uncertainty of plus or minus 0.01, plus or minus 1/100th. This has an uncertainty of plus or minus 0.1. Which has the greater uncertainty? Which uncertainty is larger? Which uncertainty is larger, the hundredth or the tenth? Okay, the uncertainty, the larger uncertainty is going to be the tenths place. So my answer has to stop in the tenths place. Or another way to look at it is this. If you line the numbers up along the decimal point, go left to right until one of the numbers stops having significant figures. That's where you have to cut off your answer. Okay? I cut the answer off after the tenths place because one of my numbers stops having significant figures after the tenths place. Now, of course, if I were to add this all together, the original number, what this would look like, it would look like 129. You put it into the calculator, it would look like 129.06. But because the last significant figure is the tenths place, I have to round this tenths place up or down based on the number that comes after it. The number that comes after it is a 6, so that 6 is going to cause that 0 to round up. That's why I get the 129.1. Yeah, so when you add or subtract numbers, you're adding and subtracting their uncertainty. So it doesn't matter how many significant figures you have, it matters where the significant figures are. Note that the first number here has 5 significant figures. The second number has only 2. But your answer has 4 significant figures. Significant figures all over the place. That's because it doesn't matter how many sig figs you have, it matters where the last significant figure is. When you're adding and subtracting, you can gain or lose sig figs. You can have more sig figs than either of the numbers you're adding, or you could have fewer sig figs than either of the numbers you're subtracting. So that's the thing to look for. Where is the last significant figure? Line them up along the decimal, go left to right until one of the numbers stops. That's where you stop. Now, another thing you can do is if you have numbers that are basically they both have decimal points, they both have decimal points in both the numbers you're adding or subtracting. The answer can have the same number of places past the decimal as whichever one has the fewest number of places past the decimal. So the answer has the same number of places past the decimal as whatever value has the fewest decimal places. So in this case, the first one has 2 decimal places, 2 digits after the decimal. Second one has 5 digits after the decimal. So your answer after you add them is going to only have 2 digits after the decimal. Does that make sense? Cool. Yeah, those are just 3 different ways of looking at it. Use whichever way makes the most sense to you. Okay, so let's go ahead. Let's go ahead and actually do a little bit of calculation here. In this case, it says most of the times when you're doing calculations, you're not going to do them by hand, right? You're going to end up putting it into your calculator, especially on a test, especially if it's like these big, awful numbers that you don't want to deal with. Well, if you're going ahead and you're adding and subtracting various weird numbers, put them into the calculator. You're going to have to round them to the appropriate number of sig figs. All right, so let's round them to the appropriate number of sig figs. What would be the answer you'd get for the first one?
0.71.
Yeah, absolutely. We have we have last significant figure in the hundredths place, last in the thousandths place. So hundredth is greater than a thousandth, so I stop my answer at 0.71. 2 decimal places versus 3. What about the next one? Well, let's look at where the last significant figure is. What's the last significant figure in the 82,000? Last significant figure going left to right.
The 2.
The 2. And what's the last significant figure in the other one?
2.
Also the 2, right? So this last significant figure, this is worth how much? What place value is that?
1,000?
Thousands.
Yeah, the thousands. And this is the hundredths, right? So which is bigger, the thousands place or the hundredths place?
The 1,000?
Thousands. Which means your answer is going to have to be rounded to the nearest thousand. So therefore the answer is going to be what?
82,000.
82,000. Does that make sense?
Yes.
Yeah,
Any questions?
explaining it that way makes that click for me.
So what about the next one? The last significant figure in the first number is which one? What place value?
0 or the tenths.
Yeah, the tenths place, right? And the last significant figure in the other one is this 2, isn't it? So your answer is going to have to stop in what place value then?
The 10th.
The tenth.
The tenths place. So the answer is going to be what?
0.1.
0.1. Be rounded to the nearest tenth. Very good. What about this last one? This last one's kind of a trick question.
0.
0. Very good. I am very impressed. Not too many students get that one. Yeah, because the last significant figure is this ones place, the tens place. Last significant figure here is in the 10,000ths place. So I have to round this to the nearest 10. But if I'm looking at this, I would never actually put the zeros in front like this, but look at this, if I'm rounding it to this, I round it up or down based on what comes after it. What comes after it is a 0. So 0 rounds 0 to 0. You're done. Does that make sense?
Yes.
You usually won't get anything that hard, but I'm very happy that you're able to do that because that means that you'll be able to do the easier stuff. Cool. Now for the easier rule, multiplying and dividing. So when you're multiplying and dividing, the product or quotient, multiplying or dividing, of 2 or more measured values must have the same number of significant figures as the measured value with the fewest significant figures. So, for example, if this number has 4 sig figs, and it does, and this one has 2 significant figures, my answer is going to have the same number of sig figs as the one with fewer, so it'll have 2 sig figs. Now this one is an easier rule to remember. It's a little bit harder to understand why, but for example, if I have, let's say, for example, 10 with, or if I rather, let me change this real quick. If I have, say, 11 centimeters, okay, times 11 centimeters, I'm trying to measure the area, say, of a rectangle. Well, 11 means the last significant figure is in this ones place, right? That means it could be a little bit less than 11, could be 10, or it could be a little bit more than 11, it could be 12. When I say 11, it's not actually 11. It's just closer to 11 than it is to maybe anything else. But there's a little bit of an estimated value. It is an estimated value there, so it's not certain. So it could be as much as 12 or as little as 10. Well, if I multiply 11 by 11, I get 121 centimeters squared. If I multiply 10 by 10, I get 100. If I multiply 12 by 12, I get 144. Okay? So you can see if you're comparing these numbers, that the first number is the same for all of them. So it's safe to say that that number would be certain. But the second number varies quite a bit. It varies from 0 to 2 to 4. So that tens place is definitely uncertain. So if I round it to the nearest tens place, then it actually makes sense that you would only have 2 significant figures. When you're multiplying and dividing uncertainty, or when you multiply and divide, you're multiplying and dividing uncertainty, which is why you have to go with the least certain measurement. And now, admittedly, though it's possible to have a number that's a little bit more significantly off, like 144, or a little bit more significantly off, like 100, usually the error is not going to be in the extreme in the same direction for every single measurement you make. Usually, if you estimate one a little bit too low, you'll maybe estimate another one a little bit higher. And so that's why we kind of use these rules for significant figures. It's an easier and quicker way than doing full-on propagation of errors. If you've never done propagation of errors, consider yourself lucky. It's basically where you keep track mathematically of every possible error you have. Significant figures is a way to make things easier, believe it or not. Because the errors are important, especially for highly sensitive equipment. Like if you're separating isotopes into radioactive versus non-radioactive isotopes, just the tiniest little error, if not taken into account, can cause the entire thing to explode because of the speeds at which these things are run. These have to be very carefully balanced. And likewise, if you're an anesthesiologist, you don't take into account errors if you don't make your measurements very precisely and give too much medicine. You can cause somebody to suffer significant organ damage because of the amount of medicine you gave them. Or to wake up in the middle of surgery, which is also fun. So there's a reason for our madness. And make no mistake, we chemists are mad. I was kidding. So let's look at the multiplication. Let's do a little practice with multiplication and division, and we'll call it a day. So, like I said, you're never probably going to do these calculations in your head or on paper. I mean, these are kind of calculations you're going to want to use a calculator for, right? I mean, I wouldn't want to calculate this times this, would you? So, how many significant figures should be in this first number?
3.
Very good, 3. So if I wanted to round that to 3 significant figures, what would that be?
49.7.
Perfect. Excellent. Good job. Now, what about the next one? How many significant figures should be in the next answer?
3.
Well, good, because this has 3 and this has 4, right? So your answer is going to have 3, and therefore this should be rounded. This should be rounded to what?
46.4.
Uh-huh. Yeah, your calculator's not going to give you the sig fig, so you have to figure that out. What about the next one? How many significant figures should the next answer have?
4.
Yeah, this one has 4, right? And this one has 6. So my answer has to have only 4. So what would that be?
The 0 is a little confusing.
Okay, so are leading zeros significant?
No.
Okay, so what should the answer be, do you think? Remember, go left to right, underline the number of sig figs you need, and then round it up or down based on the number after the last significant figure. The left to right, we'll have 1, 2, 3, 4. There's no number after the last significant figure. So this would just be exactly the way it looks. 0.05985. Does that make sense?
Well, I guess it's a little confusing because the 0 in the tens place.
Well, remember, it doesn't matter if they're leading zeros are never significant, whether there's a decimal or not. Zeros before the first non-zero number, zeros to the left of the first non-zero number are never significant.
Okay.
So you skip any initial zeros and go to the first non-zero number. That's when you start counting significant figures.
Sounds good.
Cool. Now, how many significant figures in this next one? How many in this number right here?
5,
Yeah, this has 5. How many significant figures in this one? The one on the other side.
4,
So my answer has to have
4.
4. And so what would that look like with only 4 significant figures?
Now
What would I write?
586 times
1.586 times 10 to the 7, right?
right.
I think that's what you said. I kind of cut you off. My bad.
You're fine.
All right, so very good. Yeah, absolutely. Now what about this one? How many significant figures are in this number here?
4.
3.
4. Very
Oh,
good.
and because it's wedged. Okay.
Yep, that zero's in the middle. Yep. How many significant figures are in this number here?
4.
4.
Very good. 4. And so what would I do for this number? How would I write that answer?
One point
Go on and say it. You're on the right path.
000.
Exactly, 1.000. Sometimes you'll get a situation where, and I've seen this with a lot of students, and the calculator stops short of the correct number of significant figures. So they don't put anything like, they don't put a point zero or anything like that. But if you have 4 significant figures to start with, you multiply these and you get exactly 1. You just have to remember, oh, well, I have to have 4 significant figures, so I have to express that. So I'll add the 0.000. Likewise, if you were to get a number that was like 24.1, and it was supposed to be 4 significant figures, you'd have to write it as 24.10. You'd have to add that extra significant figure at the end. Because sometimes, based on the calculations you do with the numbers, you're going to end up getting a value that's not quite the right number, like it's going to not be the correct number of sig figs because it just happens to be a perfect number that it doesn't have a bunch of, smaller numbers after it, you know? Cool. Well, any questions? Any questions for me? You guys did great. Um, the only other thing that I was going to mention after that was mixed order of operations for complex calculations involving more than one process. Do not round until the very end of the calculation, but also keep it do order of operations. So, like for example, in this case, don't add don't add this one to this one. Keep in mind that when you multiply and divide before you add and subtract. So, I mean, if you need to, you can put parentheses around it, even though the parentheses aren't there. But multiplying and dividing comes first. Adding and subtracting comes afterwards. And so you do those to get the answer with 4 significant figures. And then you would add all 3 of them together, lining them up along the decimal point. In this case, multiplying those two, you get this number, 4 significant figures, and then you have this in the tens place, this in the hundredths place, and this in the hundredths place. So your answer is going to stop in the place value of the largest uncertainty, the tenths, and you get 239.6. In a case like this, where you have parentheses, you do what's in parentheses first, take the correct number of significant figures, in this case 8.52 plus 4.1586, you're going to end up with 12.6786, although this is going to be your last significant figure because this has 2 places past the decimal, this is 4, so your answer has 2. Remember, adding and subtracting, it's where the last significant figure is. It's not how many sig figs there are. Likewise with the next one, the last significant figures, hundredths place, tenths place, you'll stop at the tenths place. You can then add those numbers, and since this would have or multiply those numbers, since this would have 4 sig figs, and this has 4 significant figures, your answer also has 4 significant figures, and therefore your answer is going to be rounded 2180 with the decimal point. Any questions over anything that we went over? Anything that I can help make better sense for you?
I think I'm good. Thank you.
Thank you for this.
Yeah, no problem. We'll plan to do a session every week to help help you understand each thing. Next week is we're going to hit conversion factors. Oh yes, you want to know where we can find the recording? I'm going to post the recording up on our website. I'll actually go ahead and show you. Let me actually show you real quick. I'm going to share my screen one more time. Our website has a ton of really cool things, and I want to share it with you. So right now, this is my organic chemistry stuff I'm working on. But so basically, our website, if you Google TCCSE Science, just put that into Google or DuckDuckGo or Bing or whatever search engine you use, and you'll come up with our website. If you click on Chemistry Web Resources, down by Introductory Chemistry, Chem 1406, actually, oops, sorry. For the recording of this session, you'll go to Workshops and Events. This has a lot of cool stuff for Chem 1406, including chapter reviews, which review all the major concepts of each and every chapter. It gives the definitions and breakdowns, like how to do scientific notation. If you're stuck on that, go step by step how you do it. It recaps some of the significant figures notes, some dimensional analysis stuff. There's equations and concepts, some nice graphics, like this one with acids and bases, etc. So the pH scale and all that. So all that stuff is available to you. There's also a comprehensive video tutorial library here that goes step by step and covers the entire textbook with a series of really good videos that we hunted down Um, I personally screened these videos to try to make sure that the videos that I was giving you are the best videos I could find. So and I tried to get a good video over every topic that you needed to have covered in your class. So the video tutorial library is pretty awesome, and there's lots and lots of really good information here. It's much better than searching on YouTube because there's a lot of bad videos on YouTube, is what I discovered. Um, and it can almost be kind of like information overload. So I kind of hunted down what I felt to be the very best. Oh, by the way, I also have a lot of practice tests and practice problems with answer keys, and they're worked out answer keys. So like you can actually do calculating with significant figures. It shows it has all the answers, etc. But like if you were to do something like metric conversions, it actually shows you all the conversions. It doesn't just give the answer, but it shows you how to work them out if you need 2 or more steps, etc. Um, but as far as the workshops and events, you can check out this page here at the top tab. Whether on every single page, if you go to the top tab up for workshops and events, if you click on that, it'll bring up this, and you can check out our archived stuff or the stuff from this semester. I will have the video for this workshop posted on our website. It'll be under Chem 1406. You can just click on that, and this has the PowerPoint that I used and the outline. I'll have a link to the video posted below this, and you can check that out as well. I'll have that posted probably sometime tomorrow. Also, if you're not patient and you don't want to wait for the most recent one, you can check out one of our archived ones as well. Because in the archive, I did this workshop previously, and we have a significant figures archive video that's present as well. You can definitely check that out. Oh, and Miss Elena, she did a workshop over the most recent lab that you are needing to do for your class. I haven't, whoops, I haven't updated that yet. And she just did it, so I'll probably be posting that video tomorrow as well. But yeah, you can definitely check out the lab videos as well from our website. Any other questions?
No, I'm good. Thank you.
You're welcome. Well, thank you so much for coming. We really appreciate it, and hope you enjoyed the session. And let me know if there's any suggestions for improvement. You can always email me at michael.depaw@tccd.edu. We'll hope to see you next week.